Hello. Today we're going to take some notes about the four main experimental chemists and physicists who contributed to our understanding of gas particles, how they move, and the math specifically that defines them. And then we'll follow up with some practice problems. So we have these four famous chemists: Robert Boyle, Charles, I'm going to forget his first name, Joseph Louis Gay-Lussac. Actually, I don't think that's an O, I think it's a U. And of course our friend Avogadro. All four of these men did very big work in the field of gases. So let's take them individually. We'll start with Robert Boyle. So, Boyle was working with pressure and volume, and he would take things like a glass chamber or a steel chamber, and put a piston in it, and inside that chamber there would be molecules of gas. I'll draw these molecules here, and he would start with them, and he would measure the pressure of these particles, and then according to the size of the chamber he would measure the volume. And then he would take that piston, so this is like some time later, and he would compress that container. He would squeeze those particles all the way down into one end of the container. Assume I drew the same number of particles there. And he would measure the new pressure in the container as well as the new volume of the container. So I'll mark those as pressure 1, volume, whoops, did that wrong. Let's make that pressure 1 and volume 1, and then pressure 2 and volume 2. And as you can imagine, in the after case, after he had compressed the piston, since the molecules had less space to move around, they had a higher pressure. So, he found the following relationship: that the pressure at the beginning divided by the volume, no, I have that wrong. He found that the pressure at the beginning multiplied by the volume at the beginning was equal to the pressure at the end multiplied by the volume at the end. Okay, and we'll go on from there. If we go to Mr. Charles, I want to say Jacques Charles, but I could be wrong about that. He was looking at heat and volume. So he would take a container, let's make it a flexible container, otherwise you wouldn't see changes in volume. And he has this balloon here, and he's going to heat it. Maybe he's got a warm fan or something. I'll draw a little flame underneath there. Obviously he's not going to use a flame because that would pop the balloon, but let's pretend. So he heats this balloon. And let's say that originally this balloon was at an initial volume and some initial temperature. And sure enough, he noticed that if you heat that balloon for long enough, it gets big. You can imagine that. The molecules are going to go faster, and they're going to hit the walls harder, and they will push that balloon until it gets to a bigger size. So it would become some new volume 2 and some new temperature 2. But he found that unlike pressure and volume are inverse relationships. Let's go back to that. As pressure went up, volume went down. This is an inverse style relationship. If we go to volume and temperature, they increase together. As you increase the temperature, you also increase the volume of the gas. So his math looked something like this. Volume 1 divided by temperature 1 equaled volume 2 divided by temperature 2. Now I'm simplifying this. We're assuming he's not changing the room's pressure or something like that, or the number of molecules of the gas. Okay, third guy. Let's keep going. We have Joseph Louis Gay-Lussac, who took, this time we're going to go back to a non-flexible container. Okay, and we'll put some gas particles in it. And he measures the pressure inside that container at some time 1, and he also measures the temperature inside that container. And then he heats his container. But unlike Mr. Charles, this is a non-flexible container. Maybe it's a metal container. Okay, maybe it's a glass container, but for whatever reason it cannot get bigger, so the volume has to remain constant. And so what we find is sometime later, this is time 2, okay, those particles have not expanded, but they are moving faster and hitting the walls harder, and so he had a new pressure, and it was a much higher pressure, and he had a new temperature because he'd been heating it, which was a higher temperature. And just like with Charles, he found that these were directly proportional. So his math looks like this. The pressure 1 divided by the temperature 1 was equal to the pressure 2 divided by the temperature 2. And you can see the similarities between the Charles experiment and the Gay-Lussac experiment. And finally, do one more, a tribute to our friend Avogadro. Avogadro was looking at, let's give a rigid container for this one as well. And now I have to be careful here that I make, let's see, 7, 8, 9, 10. Let's say I put 10 gas particles in there. And so he measured the pressure in the container, and he also measured the number of gas particles, or the number of moles. Okay? And sometime later, he didn't heat it. What he did is he added more molecules. So if I have my original 10, 2, 3, 4, 5, 6, 7, 8, 9, 10, and I'm going to put some more. There it is. I've clearly made more molecules, and you have to pretend that I drew those containers the same size, but I didn't heat them. The only thing that changed was the number of molecules, and he measured it, and sure enough, the pressure went up. You can imagine, because there's more molecules, they're going to hit the walls more frequently. So by changing the number of molecules, you change the pressure. And we saw all this in the Pogel on Friday, but his math worked like this. The pressure, first time, divided by the number of moles in the first time, was equal to the pressure second time divided by the number of moles the second time. Again, a direct relationship. So we have 4 relationships. This is Avogadro's relationship, sometimes known as Avogadro's law, that the number of moles is directly proportional to the pressure. You have Gay-Lussac's law, where the pressure and temperature are directly proportional. You have Charles's law, where the volume and temperature are directly proportional. And you have Boyle's law, that the pressure and the volume are inversely proportional. These are the only 2 factors that we see that are inverses of each other in the gas laws. Now, there's a lot of things you can do with this, but what we're going to do today is combine them all into one big law. So by now, we should be familiar, or at least comfortable with the fact that if you increase pressure, you're going to squeeze a gas into a smaller space. If you heat a gas, it will move faster and try to expand. Either it will get a bigger volume or it will get a bigger pressure. If you add more particles of gas, you will see either the container expand if it's flexible, or you will see the pressure go up if the container is not flexible. So let's get down to the math here. All of these can be combined into one, and it looks like this. The pressure and the volume are going to be on the same level, but the number of moles and the temperature will be on a different level, down below the equation. And that should all be equal to some constant. If you were to take the pressure and volume and divide it by the number of moles and the temperature, you would always get the same number for a gas. Now, in the case where those are changing, for instance, up here, we changed the volume. We adjusted the piston to change the volume. In the case like here, we adjusted the temperature. Okay? So we can also write changes for these, and they go like this. Just the first variables, P, V, over N, T, and those are all in case, or time 1. Those will be equal to the P, V, over N, T, 2. So this is what we're going to call our combined gas law equation, and it allows us to solve math problems about gases. So I'm going to show you a couple of those right now, and there's also a practice worksheet to work on after this. Keep that equation in mind. So here's a sample problem. I start with, let's do the piston problem. We'll actually put numbers to it. Start with a piston above a chamber in which I have placed some molecules of gas, and then I compress those molecules of gas like so. Okay, and there they are. I added an extra mole. Let's do that. Okay. And I'm going to go ahead and give you some variables. Let's say that when I started this on the left side here, my original container, whoops, use the right tool here. My original container had a pressure equal to 1 atmosphere, and it had a volume equal to 1 liter. Make the math simple for now. And when I compressed it, I made it half as big as it used to be. I made the volume on this side equal to half a liter. And the question would probably ask, what is the new pressure inside? How much pressure should I expect inside the container on the right? Now I have to specify in this case, I did not heat either of these, so there is no temperature change, and I did not add or take away any molecules of gas, so I'm not changing the number of moles. We will do some complex problems later where we do that, but for now, I'm just changing the pressure and I want to see what happens to the volume. Excuse me, I'm just changing the volume and I want to see what happens to the pressure. So I can use this equation that I had before. Pressure 1 times volume 1 over number of moles times temperature equal pressure volume 2 over number of moles temperature 2. But I specified that I was not changing some of those things. I was not changing temperature and I was not changing number of moles. Well, if you think about it, if the number of moles are the same on both sides, they're just going to cancel out. So I actually don't have to plug in numbers for that. If I'm not changing the temperature, it will also cancel out. This makes the equation a little bit easier to work with, because now I'm just doing, whoops, didn't change my colors here. Now I'm just doing P1 V1 equal to P2 V2. So, what I'm going to have, if I go look at my numbers here, I see that the pressure 1 was 1 atmosphere and the volume 1 was 1 liter. All right. Let me put those in to my equation. So instead of pressure 1, I will write 1 atmosphere. And instead of volume 1, I will write 1 liter. Okay, now I'm going to look at my pressure 2, volume 2. Well, I don't have a pressure 2, but I do have a volume 2. So let's plug in what I do know. I know that my volume 2 was half a liter. So I'm just going to leave pressure 2 as a variable, just like you would in algebra. And since I've got 3 givens, 3 numbers rather, and only 1 variable, I can solve for that. I just have to take and isolate that variable. So I'm going to do that. I'm going to divide by my 0.5 liters, and that should get my P2 by himself, and I have to divide on both sides. Well, I've got 1 atmosphere times 1 atmosphere. 1 times 1 is 1, divided by a half. 1 over a half is 2, so I should get 2 left. I have liters that will cancel with liters on bottom, so my only unit left over will be atmospheres, and that should be equal to pressure 2. All right, so if I go back to my original picture, I was trying to figure out what my new pressure was. Looks like it's going to be 2 atmospheres. And this should make some sense. If this was at 1 atmosphere, and I squeezed it down to this, which is half the space, I would expect the pressure to go up, and it does. It goes up to 2 atmospheres. Good. All right, let's try the second one. The second one was this guy, was this one, heating the balloons. So let's take the heating the balloons one. I've got a balloon, and I've got some gas particles inside of it. There they are. And I heat it until it expands. Here's the gas particles inside of it. And let's put some numbers to it. Let's say that originally my balloon contained a volume. Let's start with that 1 liter again. But let's say this is before I've heated it, and so the temperature is, let's say the temperature equals, let's do room temperature, which is about 300 Kelvin. It is important that you always use Kelvin when you're doing temperatures in gas. So, I'm going to go ahead and tell us, let's say after I'm done heating it, the temperature has increased by 30 Kelvin. So I'm up to 330 Kelvin. And I want to know how big that balloon is. I can do this. Well, I'm going to start with my combined gas law, which says P1V1 over N1T1 equals P2V2 over N2T2. Well, let's look. I only changed a couple of things here. I took the temperature and increased it, and I watched the volume to see if it would change. 2 things I didn't change. I did not change the pressure. We can assume the pressure is the same. And I didn't add or take away any molecules of gas. So I can say the molecules of gas will be constant. So let's cut those out. I did not change N. I did not change molecules of gas or moles of gas. And I did not change pressure. So I'm going to wind up with just volume and temperature. But notice how they're on top of each other. So volume 1 over temperature 1 equal to volume 2 over temperature 2. And now I'm just going to plug in my numbers. And I had for volume 1, I had 1 liter, and temperature 1 was 300 Kelvin. So let's put that in. 1 liter over 300 Kelvin. And my secondary variables, I had 330 Kelvin, but I didn't have a new volume. So I have to leave volume 2 as a variable. So that's volume 2, and that's 330 Kelvin. And once all my numbers are in the right place, I can do my algebra to solve. Now, I'm trying to get volume 2. I have 330 Kelvin on bottom, so if I multiply by 330 Kelvin on top on both sides, multiply, there we go, then you'll see 330 Kelvin cancels here, and I get V2 left equal to 330 times 1 over 300. That's going to reduce. I get a 0 goes away. I get 33 over 30, or I get 11 over 10, which is the same as 1.1 Kelvin. Notice my Kelvin, no, excuse me. That's not true. Oh, how do you like that? I can't delete that. Okay, it should not be Kelvin because my Kelvin up here canceled. It should be 1.1 liters. So my new volume should be 1.1 liters. Kelvin wouldn't make sense. Kelvin is not a volume term. 1.1 liters. So let's make sure that makes sense. So 1.1 liters, oops, how am I doing that? All right. 1.1 liters is the new volume. That's bigger than my original volume, which was only 1 liter. And I did heat it. I went from 300 up to 330. So this should make some sense to us. Heating the balloon will make a bigger balloon, unless I heat it too much and it pops. Okay. Let's do a big sample one. Let's go find some space here. Let's say let's do another piston problem. Here's my piston. This time I'm going to start with it compressed quite a bit. And there's some particles of gas in there. There they are. Now let's say I heat this. Okay, I heat that gas inside and it's going to bounce around faster and cause a bigger pressure or a bigger push, and that will actually cause the piston to rise up in the cylinder, creating a bigger volume. There we go. Now, before I heated it, let's say the pressure here was equal to 1.5 atmospheres, and let's say the volume was equal to 2 liters, and let's say the temperature was equal to 300 Kelvin. That's all before I heat it. Now let's say that after I heat it, we'll say the new temperature is 400 Kelvin, so a lot of heat. And we'll say that the new volume is 4 liters. And I want to know what is the new pressure. Okay, so now I've changed 2 variables. I heated it, so I got to a higher temperature, but I also expanded its volume at the same time. This is possible. So let's start with our combined gas law equation. So we have pressure 1, volume 1, moles 1, temperature 1, equal to pressure 2, volume 2, moles 2, temperature 2. But if we look, I did not change everything. In fact, there's one variable I didn't change, which is how many particles are in that chamber. Those stayed the same. So I'm going to cross off number of moles. It did not change. It's the only one that didn't. But that means I have to keep all the rest of those variables. So my equation that I will wind up solving is the pressure 1, volume 1, temperature 1 equal to pressure 2, volume 2, temperature 2. So let's plug in. For the first one, pressure 1 was 1.5, volume was 2, temperature was 300. So I'm going to put those numbers in. 1.5, 2, make sure I parentheses because they're multiplied, and 300. On the other side, we had a temperature of 400, a volume of 4, and we didn't know the pressure. So 400 was the temperature, 4 liters was the volume, and I did not know what the pressure was. Well, we can solve for that new pressure. We can do it right now. So I'm essentially, right now, I've got a pressure, and I'm multiplying by 4, dividing by 400. If you want to clear that, you have to multiply by a reciprocal. So let's clear that on both sides. Let's multiply by 400 over 4. Liters in Kelvin. And I have to do that on both sides, so I'll put 400 on top here, over 4 here. Good. Now this will obviously cancel on the right. 400 over 400, 4 over 4. And what I will get left is P equal to, then I have to solve all of this. 400 times 1.5 times 2 over 4 times 300. Well, let's see. If I'm clever, if I do 2 times 1.5, I get 3. So that would be the same as 400 times 3 on top over 4 times 300 on the bottom. I think this is going to work out very well. I have a 4 here and a 4 here. That leaves me 100. I have a 3 here and a 3 here. That leaves me 100 there. I have 100 on top and 100 on bottom. Holy cow. It all cancels. In other words, the pressure I wind up with, you can check this on your calculator, should be equal to 1 atmosphere. Let me make sure that that makes sense. So I started at a pressure of 1.5 atmospheres. That's this guy right here. And I went to a pressure of 1. That's a lower pressure. Let's see if that makes sense. Well, I did heat it. I heated it from 300 to 400, which would tend to make me think I'm gaining some pressure there. But I did also lower the volume, or increase the volume. And increasing the volume should lower the pressure. So those are at odds with each other. If I make the chamber bigger, gas particles have more room, they should collide less. But if I make them hotter, they go faster. So which one wins? Well, if you notice, I started at 300 and went to 400. That's not double. But if I start at 2 liters and I go to 4 liters, that is double. So I've doubled the volume, which is making it low, should be lowering the pressure, but I haven't doubled the temperature. I've done less than double the temperature. So I would expect the volume to be a higher contribution, which is why, sure enough, my new pressure of 1 atmosphere is lower than my old pressure of 1.5. So that's an example of a combined gas law problem. Very common. Usually, you'll notice in all 3 examples I gave, I did not change N. Usually we do not. It's very rare to see N being changed. But it can happen. So, hopefully this is useful, and I will also post a worksheet where you can practice these calculations. And you can refer back to this video as you're working on it.